All right, so let's jump in now and start talking about backpropagation, i.e. how we compute gradients in neural networks. All right, so to set the stage here, as we talked about last time, the term neural network really just means specifying one of the three ingredients of a machine learning algorithm. So remember, there were three ingredients. There was the hypothesis class, the loss function, and the optimization procedure. And it turns out that two of these are exactly the same as before. So as before in the case of softmax regression. So our loss function is still going to be cross-entropy loss. And our optimization procedure is still going to be stochastic gradient descent. Both of these exactly like last time. In other words, our actual optimization problem is exactly the same as before. It's just given by minimizing over our parameters the average of our losses, of our cross-entropy loss, between the hypothesis and our true output. The only difference is that our hypothesis class now, instead of just being a linear function, is now a neural network. Either the simple two-layer neural network or a multi-layer, L-layer network. And of course, very soon we'll talk about even more complex and structured hypotheses. So what this means is that our the only difference, practically speaking, in an implementation of a neural network versus softmax regression is that we just need a way of computing these gradients, the gradient with the theta. And when I say gradient with the theta, what I really mean, well, this will come up the next slide. What I really mean, of course, is the gradient with respect to both sets of parameters, so W1 and W2. Okay? And that's the only difference. Okay, so let's in fact jump in and actually figure out what these gradients are. And in doing so, we will derive the actual rule of backpropagation. All right, so when I say the gradient with respect to theta, what I really mean is the gradient with respect to W1, we need that thing. We need the gradient of our loss we care about. And here I'm just substituting in our hypothesis function. So let's talk about, in fact, that two-layer network I had before. Our hypothesis is, in fact, just this sigma of x times W1 all times W2. Right? That is our hypothesis. So this thing here is just h theta of x. And what we want is the gradient of this quantity with respect to W1 and with respect to W2. That's what we mean by the gradient with respect to theta, just the gradient with respect to both those two parameters. All right, so now we have nothing that we can do here but just actually do this. So we have to just sit down and do it. We're going to use the exact same techniques that we used last lecture. So if you're forgetting exactly how we did this, go back and watch that last lecture. The trick we're going to do is we're going to take partial derivatives as if all our values here were scalar valued. We're going to then look at the sizes of the resulting quantities, and we're going to then figure out what our actual gradient has to be in order to make these sizes work. In this case, so we're doing the cheating way of computing all these gradients. In this case, it starts becoming even way more important now to actually check our gradients, because now we definitely can make a lot of mistakes very easily. But these will, in fact, be all the correct gradients. And this is the last time I'm going to subject you to this. After this lecture, you will be able to safely ignore a lot of these things because you can do them all with automatic differentiation. All right, so let's first take the gradient of our loss with respect to W2. And W2 here is sort of the second layer of weights in our simple two-layer network. All right, so what is this? Well, this is going to be the derivative of the partial of the cross-entropy loss of sigma x W1, W2, and y with respect to the argument to the cross-entropy loss. So that would just be sigma, partial sigma x W1, W2, times partial of the inside thing, sigma x W1, W2, partial W2. Okay. This, though, despite the seeming complexity here, actually and again, you can feel free to go back to the slides from our previous lecture too here. This actually is exactly the same as our gradients we were computing last time for softmax regression. The only difference is instead of just having x here, we actually have sigma of x times w1, but nothing actually else changes because that's all just a constant for the partial derivative with respect to w2. So what this was going to be actually is just equal to, I'll actually use the word, the term s here, s minus iy. We used z for like the softmax applied to the last layer of the network last time. We already used z for other things now, so I'm going to use s here. S is just equal to, I should maybe write it up above to not crowd text too much. S here is just equal to normalize the exponential of h theta of x, i.e. it equals normalize exp of, well, sigma x w1 w2. Okay, so it's just basically equal to, oops, I lost some parentheses there. Let me move it back. It's just equal to basically the softmax operator applied to our final prediction of our classifier. And that's again, this is exactly the same as in the last lecture, what we saw for the gradient of the softmax, because this is just the gradient of the cross entropy loss, right? And so that term with respect to its input, so that term is exactly the same as before. And then times, well, the derivative of this thing with respect to w2 is just this term right here. So this will be times sigma x w1. All right, now how big are these things? Well, S here, that would just be the output. Remember, our class structure is k-dimensional. So the output here would be an m by k dimensional matrix. And this term here, this next term, sigma of x w1, well, that would also be m-dimensional because we're applying it to every element of our data, but then it would be m by d, right? Because d is the dimension of our essentially the activations or the hidden units after we apply our first layer. So then our next question, of course, is how do we actually compute the gradient from this? Well, we know that our gradient here, the W2, and hence also the gradient with respect to W2 of this loss, is going to be a D by K dimensional matrix, right? That actually was, if you go back a few slides, that was the size you saw of our matrix. And so to make this sizes work out here, this was, again, the exact same thing we did last time. What you will end up doing is you have to take this thing and transpose it times this thing. All right, so the final form of our gradient will just be sigma x w1 transpose times s minus iy. And iy, again, just sort of a one-hot encoding of our labels across the whole data set. Okay, so that's the easy one. Now we're going to take a deep breath here and do the next one. So what is the derivative of our cross entropy loss with respect to W1? Because we need both gradients, right? We have to update both parameters here in order to actually perform an update via gradient descent. All right, so I'm gonna just do it here. Again, as the slide says, take a deep breath, and we're gonna do it. Again, we won't have to do it too often, and there is a bit of structure, sort of method to this madness, which we'll show the next slide. But this is how we're gonna at least start doing this. All right, so we have to just sort of dig in. We want to compute this thing, and this will apply the chain rule a few different times here. All right, so I'm just going to write out what this is. So this is going to be partial L cross entropy of sigma in the numerator, x1 or w1, w2, y, all with respect to, hopefully I won't run out of space here. It's kind of hard to write this so small and stay on my screen. With respect to its argument, x. So this is actually the same thing as before, w2. Okay, so that's the same as before. But now we have the partial of sigma x w1, w2 with respect to w1. And because we have w1 here, this argument here still affects w1, so we can't just be done here. So in fact, we have to apply the chain rule some more times. And so this thing is going to be times the derivative of sigma x w1, w2, partial sigma x w1. That's a term that depends on x1. And I'll just finish out the rest here without sort of breaking down each term individually. You would next have partial sigma x w1, partial x w1 times partial x w1, partial w1. So that is actually our whole chain rule, basically factoring out everything we need to compute all the partial derivatives we want, finally ending up in terms that can all be computed basically term by term. Okay, so what are all these things? They fortunately aren't that hard to do. So this first one here, this one here, that's actually exactly the same as we saw before. So that's going to be in the same way, s minus I y. I'm going to put parentheses around this to keep everything kind of simpler here. Times, well, what's this one? Oops. What is this one here? This is the partial derivative, or just, again, the derivative of something times w2 with respect to that thing. So the derivative there is just going to be w2. Then we have this one here, right? The partial derivative of sigma of x w1 with respect to its argument. And that's actually seems a bit kind of tricky and arbitrary, but remember, sigma is just a scalar function. And that scalar function just has a derivative. And we'll just call that derivative sigma prime, right? So for the ReLU, the derivative would be actually, so the ReLU is a function that looks like this. I haven't really introduced this yet, but the function looks like this. It's 0 in this left plane, and then linear after this. And so its derivative would just be 0 here and then 1 over here. Okay. We'll get to probably more of those. You'll use that a lot more later. But basically, this derivative of sigma is just a function we can compute, right? It's just any scalar function we have. We just know its derivative, and so it's derivative. So then the partial derivative of sort of its argument with respect to its argument is just going to be the partial derivative of, or it's going to be its derivative applied to that argument, right? So it's going to be sigma prime of x w1. Right. So again, this would be, because sigma is scalar valued, this function here would also be scalar valued, so it would be a scalar value of its derivative, and we just apply that scalar function to this whole argument here. Okay, times finally the last one. Well, again, those are both matrices, so maybe in reality it's some nasty tensor, but for the sake of pretending everything is scalar here, this would just be equal to x. All right, now the really fun part. Let's talk about these sizes here. So this one here, as before, was just going to be m by k. Okay, that was the dimension of that thing. W2 is a d by k matrix. Okay. This one here, well, this matrix here is going to be m by, this one's going to be m by d. So this whole thing is also, scalar function. So this whole thing here would also be m by d. And then this quantity here would be m by n. So that's the sizes of everything. All right, so now what is the gradient we're after? What is the gradient of our loss with respect to W1? Well, again, maybe the first thing I'll write here is to sort of write the size. This thing would be a matrix the same size as W. And if you go back a few slides, what you will see is that W1 is n by d. Right? It transforms n-dimensional space to d-dimensional space as part of the first layer. So how do we get an n by d dimensional matrix from all of this stuff? Okay, well, the first thing we have to do is the only term that involves n in all of this is x there. So we're definitely going to have to take x and transpose it first. All right, and then we have other things where we want this to be, so x transpose would be m by n. I'm going to have to enter this a lot here. So this x transpose would be n by m. So whatever is inside here, we want it to be m by d. Okay, well, we already actually have one of these, right? So we already have this one, which is m by d. So let's put that in there. Sigma prime x w1. But we have to sort of multiply it with other things too. And I guess the other thing that could be in this whole sort of sequence here that could also be m by d would be this term here, would be this term times this term transpose would also be m by d. So we also have this other term. Let's ignore what we're doing with them right now, but let's talk about s minus iy times w2 transpose. That's also the right size. And we have to multiply those things together. And in fact, those matrices, so this matrix here, you know, is m by d. This one here is m by d. And so, in fact, the way we combine these two in this particular case, we just take their scalar product, their scalar multiple of each other, and then combine them that way. We don't want to multiply them; they're the same size, so all we can do is multiply them element-wise, and that ends up being the correct gradient of this all. So this note here is probably very appropriate if you're actually going through all of this. So this is our final gradient. This is the gradient with respect to W1 of everything. And you know, again, this seems, we did a lot of math to get here, right? But if you actually to implement this, you know, to implement gradient descent on this network, you basically have to write 2 or maybe 3 if you want to compute some intermediate terms. You know, compute this term first, right? And you basically have, you know, this line of Python and this line of Python, and you're kind of done. So again, despite being pretty complex math here, you can write stochastic gradient descent for a 2-layer neural network in maybe a few more, maybe 6 or 7 lines of Python code. That's amazingly powerful. Now, a few words of caution here. I don't want to do too much more of this derivatives. I have a little bit more coming up, which I admit, but I don't want to do too much more. So in some sense, hopefully the biggest takeaway from all of this for you should be to decide that you never want to do this anymore, and you just want to invest all your time learning about automatic differentiation so you don't have to do these things anymore. The second thing to keep in mind is when we start getting at these things, you really have to check this numerically, right? So again, Tianqi's going to talk about how you check things numerically in future lectures, but it would have been really, I mean, really, like, how did I really know that was going to be a scalar multiple there? There are many other ways you can possibly combine these things together. So you have to check your answers here. You have to check them numerically and make sure they're actually right whenever you get something that's this complicated. And I wouldn't be able to get these things right unless I could actually check them. So don't do it anymore, but if you do it, then check your answers. Okay. So now, presuming no one else wants to do a 3-layer network, I'm going to actually illustrate the general case of this for an L-layer network, which will actually involve some simplification at some point, though. Things will actually be simpler when we do that, not more complicated. So suppose we want to do the same thing now for an arbitrary kind of feed-forward neural network like we talked about before at the very beginning. So this is essentially a network where we have zi plus 1 is some nonlinearity applied to a linear function of the previous layer, which would be that up to L layers, and eventually the output of the network is just going to be the L plus 1th layer in this notation. Okay, so how would we actually go about deriving this? And I don't think people really want to go through the whole sort of explicit process I did last time. So what I'm going to do instead is I'm actually going to be a bit more condensed with my notation, but I'm going to basically illustrate the fact that when you do this, what you will find is that a lot of terms in your gradients and your derivatives, however you want to compute them, they end up sort of being the same no matter how many layers deep you go, or sort of you have a lot of similar terms when computing the gradients for a lot of different layers. So I want to illustrate that briefly here. All right, so let's think about a generic L layer network, feed-forward network. Again, following this sort of simple iteration here. That's what we talked about on those slides a few slides back. And suppose I wanted to compute the gradient of the loss of this network, which again would be the gradient of the loss of the Z plus 1, L plus 1th layer, because that's considered the output of the network, with respect to Wi. This would be to update my parameters, Wi. Well, all we can really do here is just kind of do it. So I'm going to be a bit more abbreviated in my notation. You'll kind of see that. But essentially, I'm going to write this out as a whole bunch of partial derivatives, where I'm not going to sort of write down the exact form of these things, but you'll see in a second this is a valid application of the chain rule. So this is going to be equal to the derivative of, I'll just write derivative partial of L. That's this whole thing here, but writing it all is it's a bit cumbersome. So the partial L, partial Z, L plus 1. Right, that's the input argument to L. Times partial ZL plus 1 partial ZL, because ZL plus 1 is a function of ZL. And if I'm going all the way back to Wi, I need to sort of separate out all these partial derivatives. Times partial ZL partial Z, oops, that's ZZ, partial ZL, ZL minus 1, etc., just all the way down, Z L minus 1, L minus 2, etc. Down to, well, partial Z, it would be I plus 2. We're trying to get down to the ith element here. So we'd have partial Z I plus 2, partial Z I plus 1, and finally partial Z I plus 1, partial Wi. Because finally, this term here, which is just this term there, depends directly on Wi. I guess through and sigma, but does not depend on Z. Does not depend on Zi. Okay. Now, the interesting thing here is if you do this a lot, so imagine I did this for, Wi minus 1, Wi minus 2, etc. What you would, of course, see is that a lot of these terms here, they end up occurring again and again, right? This term here would occur in the derivative of any Wi, less than this I, right? Like it would also occur for I minus 1, I minus 2, like this exact same term here would. And this is actually a really, really important notion. This notion that we are kind of using, we're computing intermediate products or intermediate terms that we reuse, not just when computing one gradient, but when computing kind of all the gradients we care about. That's going to be really, really important. And it's so important, in fact, in the case of neural networks. So we're actually going to give this term a name. So this whole term here, we're going to call this GI. And GI is equal to the partial derivative of our loss, I'll even write it out, of our loss of ZL plus 1 and Y with respect to Z. Actually, here I'll write GI plus 1. There is because this whole term is the down to ZI plus 1. So GI plus 1 is the partial derivative of our loss with respect to ZI plus 1. And the really interesting thing here is that there's a very simple, of course, relationship between the different GIs. Because if I had, say, GI plus 2, I didn't write the terms here, but basically GI plus 2 would involve, all the terms up to this one. And then to compute GI, you just multiply by this last term here as well. And the way we can write this kind of formally is to say that GI is equal to, go back to blue, GI plus 1 times the partial derivative of ZI plus 1 partial ZI. Again, treating everything as a scalar here, doing all our hacks still. We'll, in the next slide, talk about the actual sizes of these things. But this is sort of the relationship, even in the scalar case. It would be in the scalar case. So we have this very nice relationship between these things, and we're going to compute these things again and again. So rather than computing them all from scratch, let's just compute them this way. Let's compute them kind of in an iterative fashion like this. In fact, we can write this out more explicitly. So now we can sort of write out, what is ZI plus 1 here? So what is this ZI plus 1? Well, this is the exact expression for it up here. So let's be a little bit more precise and actually write out what these things really are. So this would really be GI plus 1 times, well, we're going to apply the chain rule one time here, and we're going to get partial sigma ZI WI, partial ZI WI, partial ZI WI, partial ZI. Okay, so that's just applying the chain rule to this expression here, to this expression. And finally, let's now do them. We can use the exact same logic as we did on the previous slide, but actually quite a bit more straightforward, I think, in this case. What would this term be? Well, this term, again, is just the derivative of a scalar nonlinearity with respect to that argument. So this thing, well, of course, this one doesn't change. So you still just have GI plus 1 there. The next one, though, would just be, well, it's just going to be sigma prime of the argument, ZI WI. And what would then this one be here? This last one would be the partial of ZI WI with the ZI. So that would just be WI. Okay, and that is our expression for basically our recurrence that shows how to form GI as a function of GI plus 1. All right, but this is still kind of using our cheating notation. These are all treated as scalars. What do we really do here? So let's talk now about how we can actually use these operations to compute not just sort of the pretend scalar gradients, but the real gradients using the same tricks of size matching that we did before. And this, I promise you, will be the last time we do this, at least the last time you do it for a whole derivative, not just for sort of individual operations in automatic differentiation. Okay, so let's first talk about what these GIs actually are. Okay, so these GIs, the way I defined them, it was the derivative of our loss with respect to ZI, right? GI would be, right? GI would be the derivative, of the partial derivative, whatever of our loss with respect to ZI. But if we think about this as an actual quantity, what we would actually be computing here would be, what we want to store here would be the gradient with respect to ZI of this loss, right? This is just, now I'm just writing these things kind of as, when you compute the gradient, what this really is when you compute these partial derivatives kind of cheating, what you're really after here is the gradient. So what we're really after here is the gradient of our loss, ZL plus 1, and Y with respect to ZI. And the key point I want to emphasize here is the size of this thing. All right, so the size of ZI, remember, was actually, and this is, I kind of went over briefly here about like what size, what dimension ZI was. But if you go back a few other slides, what you'll see is that ZI was actually M rows, because we had one, again, ZI kind of describes those hidden units or the activations for every single example in our data set. Or in our batch, if you do it by batch, etc. And it was by Ni, because the dimensionality of each row was Ni dimensions. Okay, so that's means, of course, that our gradient of our loss with respect to ZI should also be that same size. It should be M by Ni. All right, so let's now use our logic here to So use our logic here to figure out, what the GI sort of backward iteration really should be, not in terms of sort of, scale, if everything was scalar, but if these things are actually matrices. Okay, so GI, just copying what we had in the last slide, I have to sort of count on me on this, that I'm copying correctly here. It was GI plus 1 times sigma prime ZI WI times WI. All right, and let's do our thing one more time. Well, actually, maybe not quite. We're gonna do it again in the next half of this slide too. But GI plus 1, well, that would be actually, that's going to be the same size as, for our next vector, what that will be. So that will be m by ni plus 1. Okay, that's the size of GI. The size of sigma, ZI, WI, is actually the same thing, because, right, that's the same, the size of our ZI after we had then applied WI would be the same as the size. So this would be m by ni plus 1. And this last one here, WI, is just ni by ni plus 1. Okay, so again, deep breath. Hopefully, not sweating too much here as we go through all of this. This thing would be equal to, well, how do we make these fit? Well, we know we want our final thing to be some m-dimensional thing by, some m-dimensional thing by ni. The only way we can get an ni term at the end is if we have something here times wi transpose. That's the only thing that has an ni. We have an ni as the last dimension. And then we have something here. So this, right, so this term here would be ni plus 1 by ni. So in here, we need something which is m by ni plus 1. And actually, just in the same way that we did this for the 2-layer case, the thing we actually do to make, these are in fact both that size, right? These are both the size we want there. So what you do is you just take their element-wise multiplication. Again, that actually comes out because sigma is also applied element-wise, but what this ends up being is just GI plus 1 Hadamard, or element-wise multiplication, with sigma prime ZI WI. Okay, so that's the actual, this thing here is the actual update for GIs. If you want to not just sort of conceptualize it, but actually implement it in matrix operations, this is the update you need. Okay, almost there. We have the backward iteration for the G's now in real matrix arithmetic, but we also need to compute the gradient we want, which is the gradient with respect to the parameters. That's what we actually need in order to compute our updates. Okay, so what is that? Well, that is the parameter up that we want, of course, would be this size here, right? We want something which is ni by ni plus 1. So let's just write out, what this gradient actually is. Well, again, actually, just taking the question from the previous slide, you can go back to look to make sure that I'm copying them correctly here. But this would be gi plus 1 times partial zi plus 1 partial wi. But that would be equal to gi plus 1 times partial, well, let's just plug in the definition of what zi plus 1 there. It would be partial sigma zi wi, very similar to actually to the past expression we had too, partial zi wi times partial zi wi partial wi. All right, and that's going to equal gi times sigma prime zi wi. A lot of terms are the same as before, of course, times, sorry, it's gi plus 1. Erase that there. Gi plus 1 times zi. The only difference between this and the past expression is that because we're differentiating now with respect to wi, you get zi here, right? Because it's this product with respect to wi. Right. Other than that, it actually ends up being the same. kind of hiding it with my head, I realized that, but we won't need it soon. Okay, so now let's I'll duck down here and we'll write out the sizes for this. Okay, so this one here is going to be same as before. It's going to be m by ni plus 1. This one here is also m by ni plus 1. And this one's the only difference thing we have from last time. This is going to be m by ni. Okay. All right. So now, how do we arrange these sized matrices to add up to this size? Well, hopefully I won't belabor this point too much, but what you have to do is we need an ni first, so you have to take zi and transpose it first. Zi transpose times, really it ends up being, it's this product here, which actually is exactly the same thing as we had before, and it ends up being the same product as before. So it would be this times gi plus 1, element-wise product with sigma prime zi wi. Right, and that is in fact the gradient we are after. Okay, so now we actually have done everything you need to compute all your gradients for an arbitrary L-layer network. I've told you how to compute not just like the theoretical gradients, but the actual gradient, the actual sizes of these different matrices here, right? So for all the actual parameters here in actual matrix arithmetic, how to do this. And this is maybe a bit more complicated than you've seen before. So I wanted to sort of take a pause for a moment here and argue about kind of why I've done it this way. A lot of times you will see gradients for neural networks kind of written out element by element. So, you just because scalars are easy to work with, you'll have derivatives of different terms, the different individual terms of WI that will involve a lot of sums and stuff like this. But the reality is no one would actually ever implement it that way, right? I mean, no one would implement it anyway because everyone's going to automatic differentiation. But even if you were really implementing kind of backpropagation like this from scratch, and I'll talk about why the name is called backpropagation in a second, you would implement it always using matrix operations. And so what I really want to do from the start here is show you how to derive those actual matrix expressions, because you're going to do little pieces of that when you do the equivalent matrix operations in automatic differentiation. So even though this may seem in some sense more confusing, we're taking weird sizes and making them fit by this really hacky way. That is hacky, I admit, but there really is a reason why we're doing it this way. It's much better to learn how these things actually work and work in a way that we actually would implement them than sort of derive each individual expression out in a way that no one would ever actually implement it as. All right, so with all this being said, what is the final form for our algorithm? Now, this sort of way of computing gradients goes by the name backpropagation, right? And backpropagation is typically framed as having two different passes over the layers of our network, a forward pass and a backward pass, which basically compute in the forward pass the zi terms and in the backward pass the gi terms. So making this a bit explicit, the way we compute the forward pass, and backpropagation is a way of computing all these gradients. So the way we compute the forward pass is we first just initialize our first layer to just be our input, right? That's kind of convention. We just make our first layer equal to our input, really so we can use the same notation for all subsequent layers. Then we form our iteration here of zi plus 1 equals sigma I of zi wi from I equals 1 to L. By the way, just to reemphasize this again, I had my nonlinearity here vary by I, and frequently the last layer would just not even have nonlinearity, it would just be a linear layer, but that's just details. You can really actually do whatever you want in this formulation. Okay, so this computation of the actual output is called the forward pass of the network, or of backpropagation, or forward pass to the network. The backward pass, and sometimes actually just the backward pass is referred to as backpropagation, though whether you call both the forward backward pass propagation, actually what you even call backpropagation is a bit odd. Like, is automatic differentiation actually doing backpropagation or not? I think even actually Tianqi and I use slightly different terminology here, so be aware there's no like single definition of this, but other than to say that backprop is the way that you actually compute gradients here. What the backward pass does is it initializes first of all, the last backward gradient, which would just be the gradient of the loss with respect to, the last unit itself. In the case, I should sort of qualify this, in the case of cross entropy loss, this would actually be equal to that S minus IY term you saw before. So you take the output, form the softmax, that becomes S, subtract off the one hot encoding. That's the first term, GI, or GL plus 1. And then you perform the backward updates on the GIs as we exactly derived in the previous slide. So that is just the previous slide here. That is just this update here for those. All right. And finally, you do this from L, you do this in reverse order. So you do it from I equals L to 1. And then as you go, as you do this, you can also, of course, compute the gradients, which again was exactly what we had on the last page, of the parameters. Now, the important thing to keep in mind here is this sort of computes simultaneously all the parameters in one forward pass and one backward pass, right? Because we can kind of use these GI terms and the ZI terms to compute all these needed gradients. But to do that, we need to sort of cache things along the way, right? We need to sort of compute this term, these GI terms, to kind of reuse them. We're not going to kind of form them from scratch. And so really, in some broader sense, all backpropagation is just the chain rule and intelligent caching of the intermediate results. And that's what backpropagation is. Now, one important point that I want to highlight on this is that let's look at the form that is required to compute the gradient with respect to Wi of our loss. And notice that it contains terms both Zi and Gi. And what this means is that to compute this gradient, we can actually kind of do it along the way in our backward pass, but we had to store the Zi's. We can't throw away any of the intermediate terms in the forward pass. We have to keep them around so that we can use them to compute part of our backward gradient. And so even though this is sort of efficient from the standpoint of we're making one forward pass in the network and one backward pass, it ends up being actually just twice the complexity of a single forward pass. It's much less memory efficient in some sense because we have to store all our items along the way. We can't, if I was just kind of compute the output, right? I could actually, once I computed Zi plus 1, I could throw out Zi, but I can't do that here. And this notion of maintaining intermediate elements in this forward and backward pass is actually really crucial to backpropagation and becomes one of the chief kind of trade-offs of backpropagation. It's allowing for more efficient computation of gradients at the cost, sometimes, of more memory storage. So that's not really a preview for sort of later things, but just keep that in mind when we talk about actually how efficient backpropagation is. It is very efficient computationally, but it does incur, at least naively speaking, does incur some added memory cost. All right, so with that being said, I have only one slide left to talk about, which is to say the following. So that's generic backprop for multi-layer neural networks in true matrix form. And I do think it's fair to say that most kind of machine learning courses that discuss backprop, they often end there, right? They sort of say, here's how you derive back. Maybe they'll talk about convolutions, but they also don't even talk about how you derive backprop for a convolution. They just talk about, the forward pass of a convolution and assume it's all sort of works out. When we talk about actual backprop, most classes kind of stop there. Maybe they don't even quite get there because they don't even get to matrix form, but they kind of get there, and then that's deep networks. That's the end of it. And for us, of course, that's the start of it, right? And in fact, it's not how we're going to do it in any more of this class. So the last thing I want to leave you with before we never see these things again is to think a bit more about what's in some sense really happening in the backwards iteration. So to compute, this gradient here, gradient with respect to Wi of a term. Of course, I'm writing its partial derivative now, but really it's a gradient. What we need to do is we sort of had this term Gi plus 1, and we multiplied it by the individual terms, of course, broken down with the chain rule, but basically we had to multiply it by these terms here that involve just the derivatives of the ith layer. And one way to view this is, what was the job of the ith layer in some sense, right? Well, the ith layer, first of all, it had to compute itself, right? I had to know how to compute the ith layer. But it also, if you just sort of talk about like what's the responsibility of the ith layer, and that's a very weird, maybe odd way of phrasing it, but its responsibility is first to be able to compute kind of, its forward pass, right? Compute its layer, compute itself. And it also had to take this term here, this, what I'll call this like incoming backward gradient, gi plus 1, and multiply it by its own derivatives, the derivative of zi plus 1 partial wi, right? Really this is actually some big sort of Jacobian thing, but ignoring that for a second, it had to actually figure out how to multiply this thing by this thing and whatever size actually made sense here. And this is actually a crucial insight into making this whole procedure more modular, because this is a very general statement. Generally speaking, all that any layer has to be able to do in order to fit into a backpropagation framework is be able to multiply the incoming backward gradient with its own derivatives. In fact, this is such a common thing that it has its own name, and this is an operation called the vector Jacobian product. That term is actually quite misleading because gi in reality is not actually a vector, but what that really means is if you think of this whole thing as a vector, and you think of this thing really in multivariate calculus as what's called a Jacobian, this operation, multiplying this thing here by this thing, that is what's called a vector Jacobian product. And the very interesting thing is that this process can be made much more modular and much more general. And this is exactly the process that we're going to cover next lecture. Maybe not in full generality, but over the next few lectures, and of course also in the homework assignments. This is exactly the process you will cover when it comes to automatic differentiation, which then beautifully will sort of avoid the need for any of this hacky math and kind of manual application of the chain rule to the point where you start to sweat. So you have to do it. It's good to do it once. It's good to go through the exercise of manually deriving backprop for a multilayer neural network once. Now, shell it away, and let's start next time talking about automatic differentiation, or how we really do this in practice.